Alrighty, looks like we might be live. Yeah, looks like we are good to go. Alright, I'm going to be trying something new throughout the course of this video. Basically over this last week, I was just thinking about how I want to consistently learn more about weather, but I don't exactly feel like I have been doing that, so I decided to come up with a format where I can just learn about weather every single day. And this is the format that I'm started with. Let me know what you think. But I'm basically just going to go online, try to figure out some new stuff about weather. I'm going to do it live. And then while I'm doing it live, I'll also do little summaries as we learn new things. And then I'll upload these as shorts later, so you can just get the key highlights in little 1-minute summaries. But I do just want to make sure that we're live. Yes, we are. So I have my iPad pulled up on the side here. So if you guys have any questions that you want me to look up, if you're on the live stream, then feel free to just fire off those questions. In the meantime, I'll just look up the first thing that I want to know more about. And the main tool that we're going to be using today is ChatGPT. If you don't know about this, it is an unbelievable tool where you can basically type in any question and any format that you want that question answered in, and it gives it to you. So for example, main thing I need to learn more about but I don't know enough about is atmospheric rivers. So I'm going to say, write a 300-word essay on atmospheric rivers. Hopefully as I do these more, I'll be able to start typing faster. I see Robert's on the live chat. Good to see Robert. If you have any little weather questions that you'd like me to look up, feel free to fire them off. Snowstorm for CT. Is that CT Connecticut? Alright, so we're getting our first little answer here. So I'm going to just read this, and then we'll be able to turn this into bullet points, and then I might even turn it into a little short story poem too. Alright, so main question I have is what are atmospheric rivers? So atmospheric rivers are long, narrow bands of moisture in the atmosphere that can transport large amounts of water vapor over long distances. Alright, so that's a bit wordy. So let's actually just look up what an atmospheric river looks like, so we can get kind of the picture of what's going on here. See Lucy's on the live chat too. Good to see Lucy. All right, so this is one of the best pictures I've ever seen for an atmospheric river. So this won't be copyrighted, which is good because it's from a government website. But let's see. Atmospheric rivers are relatively long, narrow regions in the atmosphere, like rivers in the sky. Okay, I really like that description right there, like rivers in the sky. And the reason I wanted to look this up is because we just had a really big rainstorm in California, and it wasn't one of the atmospheric rivers, but somebody asked me that, and they're like, what exactly is an atmospheric river? And as a broadcast meteorologist in California, that is one of the questions I should perfectly know the answer to. And I kind of knew what to say. I actually said something along the lines of, it's sort of like a river in the sky. And I knew that about 90% of California's rainfall every year comes from about 5 big atmospheric river events. Now, we're going to have to fact check that one, but I'm pretty sure that's true. Hopefully that's answered within this page that we're on right now. All right, so it transports most of the water vapor outside of the tropics. These columns of vapor move with the weather, carrying amount of water vapor roughly equivalent to the average flow of water at the mouth of the Mississippi River. So that seems like it's basically saying it's like the Mississippi River, but it's in the sky. So it's not a big surprise that this is where California gets a lot of its rainfall. And then it goes on to say, when the atmospheric rivers make landfall, they often release this water vapor in the form of rain or snow. And a big part of this is also going to come down to the rain shadow effect. So if you haven't seen it, I just did an explainer video on my channel about the rain shadow effect. But we'll just use one of their pictures right here, where rain shadow effect is where you get water vapor being pushed in over a mountain. And the wind can't just go directly through the mountain, so it's pushed up. Now as that air goes up, that what was warm, moist air starts to cool down, because as you go higher up in the atmosphere, it gets colder. Just think if you were to open a plane window, it would probably be freezing. And as it gets colder, it just can't hold as much water vapor, so that water vapor turns into clouds. You get a bunch of rain and snow on this side of the mountains, and then on the back end, a lot of that water vapor has been squeezed out. So you get that rain shadow, where you often have deserts on this other side of the mountain range. So that's part of what's happening in California, where we get this big river. One second. Yeah, let's get that person out of the chat. Good thing we got our moderators on here. Great job, Lucy and Robert. So basically what's happening with these atmospheric rivers is you get one of these rivers pushing into California, and then we have some mountains in California. So first it's going to be squeezed out over places like Santa Cruz, and then it's going to drop into the Central Valley, and then even more is squeezed out once it gets up into the Sierra, which you can perfectly see right here. So, although atmospheric rivers come in many shapes and sizes, those that contain the largest amount of water vapor and the strongest winds can create extreme rainfall and floods, often stalling over watersheds vulnerable to flooding. So, might have to look up some flooding information too later in this video. These events can disrupt travel, induce mudslides, and cause catastrophic damage to life and property. So that kind of answers the question of why do we need to know about this? And right there, that kind of answers it. This is where California gets most of its rain, but that on the flip side of that means it's also where we get most of our flooding and some of the damages that we get with these big storms that come in. So a well-known example is the Pineapple Express. It's also a movie, one of my favorite movies from high school. A strong atmospheric river that is capable of bringing moisture from the tropics near Hawaii over to the U.S. West Coast. So let's see the science behind atmospheric rivers. I think this might be the graphic that explains how much of California's annual rainfall comes from these events. So, and then after we do this, we'll get back to ChatGPT and see if it can just summarize it in some bullets for us. So an atmospheric river is a flowing column of condensed water vapor in the atmosphere responsible for producing significant levels of rain and snow, especially in the western United States. So the main thing that I always look at is California weather and wildfire. So if you're thinking about weather in California, atmospheric rivers are one of the most important things that you have to know about. So when ARs move inland and sweep over the mountains, the water vapor rises and cools to create heavy precipitation. So that's that rain shadow effect that we were just talking about right there. You can kind of see it in this graphic where it rises up the Sierra, the water vapor cools, and then it's almost like a sponge. If you were to just have your sponge filled with water and just squeeze it, that rain's going to fall. And then if it's high enough, it's cold enough for that precipitation to fall as snow. And that last storm that we just had was pretty awesome. We picked up, we picked up 37 inches of snow over the span of 24 hours, which was a record for whichever resort that was. So yeah, that was a pretty great storm that we picked up. Santa Cruz Mountains, I saw a few readings that were around 6 to 7 inches over the course of 4 or 5 days. And one of the big reservoirs up there actually doubled over the course of 5 days. So we went from, I think, 18% of the reservoir being full, which is pretty bad and is actually a little bit scary, to like 36% of the reservoir was full just from one storm. And we're still pretty early in the season. It's only December 15th. So we have a ways to go. Hopefully a lot more storms to come. I think the main thing that I'm hoping that doesn't happen is what happens last year. If you remember last year, we had just an awesome December. We picked up a massive amount of rainfall, and then it basically didn't rain all of January and February. And then, what do you know, we started wildfire season with pretty dry, record dry fuels, very bad drought conditions. Now, when it comes to wildfire season, though, it ended up being not a bad year. It was a below average year. And I think it was 2 million less acres than previous years. Let's actually just look that up because I want to see what the update on that is. Now that I feel like it's safe to say that wildfire season's over, especially with that last storm. I mean, knock on wood, everybody watching. But with that last storm that came through, that was pretty great to see. And a lot of that moisture works its way into our fuels. All right, this is the graphic I was looking for. So 2022 combined year to date, we had a lot of fires, almost 7,577 acres burned. Wow, it's almost unbelievable that that's actually the amount of acres burned this year. So 362,478. So 2021, to put that in perspective, about 500 less fires burned, but we had 2.5 million acres burned. And then on the 5-year average, we had 8,000 fires roughly per year, and then over 2 million acres burned. So this year, we had about 2 million less acres burned than previous years. That's pretty awesome to see, especially considering the fact that we went into this wildfire season with such bad fuel conditions. I remember looking at some of the fuel moisture readings, and we had record dry fuels. And then drought conditions were also just about as bad as they could be. And ended up not being a bad year. Now, what would be the reason for that? Well, one of the big reasons for that is a few of our big fires that we had. I believe it was like the mosquito fire, and there was another big fire. But both of them got rained on after like 2 days. And the fires were just about ready to take off. And then some lucky big rain events came in and just put those fires out. So that's a big part of the reason that this number right here is as good as it is. All right, so what is the main thing that we just learned? We just learned that this wildfire season didn't actually end up being all that bad. Last year we had about 2.5 million acres burned. The 5-year average was about 2.2 million acres. And then this year we only burned about 360,000 acres. Now we had very dry fuels, we had very bad drought conditions, but a few of those big fires that we had ended up getting rained on. So it ended up being a pretty good year for us when it comes to wildfire. And now that we're seeing some big storms moving in, it looks like most of that wildfire threat is behind us, and we can just look forward to California picking up more rainfall. All right, so that's overall pretty great news right there. Let's get back to what we were learning about with some atmospheric rivers. I see Lucy's asking some questions. I'm curious about the extended forecast the Bay Area stations are saying next Wednesday. Yeah, let's take a little break, check out the weather forecast. I probably should just know what's going on in the weather forecast at all times. And I haven't looked at it very much this week, so we'll be kind of figuring out what's going on together. So let's go forecast slideshow, ECMWF, and let's go to California. First thing I always like to do is just to see, let's just go straight to precipitation. That's the main question we have. When's the rain coming in? All right, doesn't look like much. So this is through Saturday, Sunday. Maybe a few scattered showers showing up Monday, Tuesday. A little snow as we get into Tuesday. More showers throughout parts of Northern California through Wednesday, Thursday. Little heavier rainfall on Friday, and then this is pretty much the point in the forecast where I stop trusting it. So right there, doesn't look like there's a good storm set for California. The other thing that I always like to do is look at the CPC outlooks. And I would say that these are actually pretty... It gives a basic idea of whether it's above average or below average chance at precipitation. Right now, it looks like 6 to 10 days out are supposed to be warmer than average. 8 to 14 days out, looks like we're warmer than average. All right, so usually that's not a good sign when it comes to rain. Usually rain is associated with those cooler conditions. Yeah, so 6 to 10 days out, most of California is in that drier than average category. 8 to 14, yeah, still dry. All right, so that's not the best news, but we did already pick up some good rainfall. So something else that we can check out here is, let's go to YouTube. Let's see, I'm not signed in, so we're gonna go to Holt Hanley drought. I did this one drought video. I don't remember when it was, but I remember I had some good links in this video. So that's the link I'm looking for. This is how I save links. I create videos and then I remember what links I used in each video. All right, so this is going to look like a lot of data, but we can actually break it down pretty well. So if anybody watching has a city you want me to look for in here, I can try to check it out. We'll start off with, we'll go to Redding first. So Redding, on average for the rainfall season, has about 8 inches of rainfall at this point. So rainfall season starts at about October 1st and then we're going to yesterday, which is December 14th. On average, they have about 8. Right now, they've picked up 5, so they're at about 66% of normal. How about San Francisco? On average, they're about 5. They've picked up 4, so they're about 73% of normal. So looks like most of the Northern California cities are about 50-50. Some look like they're below average. Some look like they're above average. Now, if we go to Central California, this is where things start to look a little bit better. One of the spots I've been checking out has been Salinas. On average, it's about 2.5 inches. We picked up 3.7, so 136% above average rainfall for this point in the year. Then when you look at Stockton, Modesto, Merced, those are all at about 150%. Same with Fresno and Hanford. And then Paso Robles is about 200%. So pretty great start to the rainfall season for Central California. And then Southern California almost looks like it's doing even better. Almost all of these cities down here, including Los Angeles, that's at about 145% of the rainfall you would expect at this point in the year. A lot of parts of San Diego, 100 to 105. So not a bad start to the rainfall season. And now we'll get back to atmospheric rivers because this is the main thing that we're going to be looking for as we go further. I always forget which one it is. As we go further into the rainfall season, if we haven't had one of these big atmospheric rivers yet. We've had some good storms, but not one of those big, massive atmospheric river events that unfortunately can lead to flooding, but also just jacks up our reservoir levels. So let's continue looking at this. So got a little sidetracked as we were talking about how it rises up the Sierra, it cools down, and then it squeezes out all that rain. And then let's continue this. It says, though many atmospheric rivers are weak systems that simply provide beneficial rain or snow, some of the larger, more powerful ARs can create extreme rainfall and floods capable of disrupting travel, inducing mudslides, and causing catastrophic damage to life and property. So it's interesting how many things in weather work both ways. So, for example, with wildfire, obviously wildfire is bad for obvious reasons. It can destroy houses, it can take people's lives, can basically just take everything people have worked so hard to acquire throughout their lives. It can, in the very extreme wildfires, it can just destroy entire ecosystems. The air quality impacts people. Sometimes the air quality is actually the worst part of a wildfire that affects the largest amount of people. But then on the flip side, wildfires are also very beneficial for the ecosystem in a lot of cases. It's able to clear out a lot of the fuels. and then clear out a lot of the vegetation. So the vegetation that's left there is going to have access to a lot more water. One way to think about that is if you have 100 trees in an area that should be sustaining 20 trees, and a wildfire comes through and it burns 80 trees, that's actually going to be good for the 20 trees that survive, because before they weren't getting enough water, now they have less competition, and they're going to be a lot healthier. So, and then a lot of the undergrowth has been cleared out, so then new plants are able to grow and thrive. So that's where wildfire is often good and bad, and the same thing goes for atmospheric rivers. It brings us a lot of rain, a lot of snow, but then on the flip side, right there, it said it. It can lead to extreme rainfall and flooding, disrupt travel, induce mudslides, and lead to catastrophic damage to life and property. So now let's read these little facts it has right here, because I think these are going to be the most interesting part of the video that we've seen so far. So it says a strong atmospheric river transports an amount of water vapor roughly equivalent to 7.5 to 15 times the average flow of water at the mouth of the Mississippi River. Wow. So a strong atmospheric river has basically 7.5 to 15 times the average flow of the Mississippi River. That's actually unbelievable to hear about. But I guess it makes sense, because a lot of times these atmospheric rivers will be very wide. Like if we look up atmospheric rivers, water vapor imagery, sometimes it looks like it's taking up like half the state. I think this is a pretty good picture right here. So I can't really see what the underlying map is right there, but that's pretty good in picture of what it looks like, where you just have basically what looks like a river flowing in over California. And the point I'm trying to make with this is Mississippi River from this angle would look very skinny. So even though this water vapor is a lot more spread out, it's spread out enough, and there's enough of it that the overall flow is greater than the Mississippi River. Pretty interesting. All right, so now let's see. Atmospheric rivers are a primary feature in the entire global water cycle and are tied closely to both water supply and flood risks, particularly in the western U.S. Wouldn't exactly say that one's too surprising. Kind of a lot of the same stuff that we've been reading about so far. All right, I think this was the fact that I mentioned at the beginning of the video, and if you're still watching, you'll see that I was actually wrong about this fact at the beginning of the video. So this is part of the reason that I'm doing just this live stream. Just trying to figure out some new weather information and in some cases correct the information that I thought I had correctly but was in fact wrong. So on average, about 30 to 50% of annual precipitation on the West Coast occurs in just a few atmospheric river events and contributes to the water supply and flooding risk. All right, so I think originally I'd said 90% of California's rain comes from 5 atmospheric rivers. Not exactly, but the fact is still pretty crazy. It's up to half of our annual rain comes from just a few big storms. It's maybe not as extreme as the original fact that I said incorrectly, but it's still pretty interesting. Now, these next two atmospheric rivers are approximately 250 to 375 miles wide on average. So that comes back to that point I was trying to make about how even though the water's not as dense as the Mississippi, obviously you couldn't just actually have a river up above or in the sky, but it's so wide, 250 to 375 miles wide, that's where it can transport 7.5 to 15 times more flow than the Mississippi. This one, ARs move with the weather and are present somewhere on Earth at any given time. That's kind of interesting, didn't know that. And this final one, scientists' improved understanding of atmospheric rivers has come from roughly a decade of scientific studies that are observations from satellites, radar, and aircraft, as well as the latest numerical weather models. More studies are underway, including a 2015 scientific mission that added data from instruments aboard a NOAA ship. Okay. And actually, one of my good friends at San Jose State, during the graduate program, main thing I was studying was wildfire. But one of my buddies did do his project on atmospheric rivers, and it was very interesting because as a forecaster in California, or even just someone who lives here, it is super important to know about atmospheric rivers, because if that's where 30 to 50% of our rainfall is coming from, and it can lead to catastrophic damages to life and property, mudslides, disrupt travel, that's one of the main things that you need to know about. Especially if it only happens maybe 3 to 5 times per year. Those, like if you're a basketball player, the times when you need to focus the most, that's like the NBA championships. Or for a football player, it's the Super Bowl. For a weather forecaster in California, it's atmospheric river events. I think that's a good way to put it. All right, so let's just try to summarize what we have learned so far about atmospheric rivers. So atmospheric rivers are basically like a river in the air, and it transports 7.5 to 15 times the annual flow of the Mississippi, and about 30 to 50% of annual rainfall on the West Coast comes from just a few atmospheric river events. And why are these important? If you get that much rainfall over such a short period of time, that's where it can lead to some extreme flooding, catastrophic damages to life and property. But on the flip side, can also bring large amounts of rain and snow to California, which is always something that we need. All right, so I think that was satisfactory for the atmospheric rivers. Now, there's a little more information here. We might as well just keep it going. Not all atmospheric rivers cause damage. Most are weak systems. Yeah, I feel like we're kind of going over the same stuff. So what we're going to do is try to make this a little bit fun. I'm sure this is all the same information we've just learned, so I don't want to read all of that. This is ChatGPT. I said, write a 300-word essay on atmospheric rivers. It did it, but instead of reading it, let's say, turn this into a short story poem that rhymes. I don't know about anybody watching, but when I was a kid, I always learned things way better through if there was some kind of like a poem or a rhyme. I remember there was the photosynthesis song, and I didn't read like the textbook that much as a little kid, but I memorized this song, and from the song I knew basically everything there was to know about photosynthesis. So this is one of the main things I've been, it's kind of funny, but this is one of the main things I've been doing with ChatGPT. I'll look up something I'm interested in, like atmospheric rivers. Sometimes I'll read it, but then I'll say, turn it into a short story poem that rhymes, because then it's often much easier to understand and much easier to remember. And I'd imagine this comes from human beings just passing down knowledge for such a long period of time through either stories or songs. So I'd imagine our brain evolved to just kind of learn from stories and songs. So let's see this atmospheric river poem. So it says, atmospheric rivers are a sight to see, long and narrow, transporting water over land and sea. They form when moist air is lifted high, releasing its moisture from the sky. These rivers play a crucial role in the global distribution of water and the water cycle's goal. But they can also bring storms and flooding, it's true, leading to landslides and natural disasters. That much is true. Kind of rhymed true with true there. That's an easy one. Climate change has increased their frequency and intensity, exacerbating their impact, it's clear to see. But scientists are studying these rivers with care to better understand and predict their movements to better prepare. Oh, well, I kind of like that one, that verse right there. For the potential impacts of atmospheric rivers, we must try to mitigate and prepare so we don't have to say goodbye. That's kind of dark. To the land and people affected by their might, we'll work to understand them day and night. All right. That all kind of made sense. I think the line I didn't know is climate change has increased their frequency and intensity. So let's look that up. How much has the frequency and intensity of atmospheric rivers gone up with climate change? I wonder if there's some studies about this. Usually it takes just a second or two to come through. I'll take a quick look at the live chat. Yeah, looks like Robert and Lucy are still on. Great moderators. All right, so we have some interesting information here. All right, so the question I asked was, how much has the frequency and intensity of atmospheric rivers gone up with climate change? Because that was one of the lines here in the poems. So frequency and intensity of atmospheric rivers has been found to increase with climate change, although the extent of this increase is not fully understood and is the subject of ongoing research. So atmospheric rivers are fueled by warm, moist air, and as the Earth's surface warms, the atmosphere is able to hold more moisture. Okay, so what it's saying there, it actually ties into the rain shadow effect that we were talking about earlier, where as air is pushed up and over a mountain, it cools down because it's going higher up in the atmosphere. And as it cools down, it can't hold as much water vapor, so it squeezes that water vapor into clouds and then rain. So that's why up in the mountains, you get a lot more rain and snow than just on the backside of the mountains where that moisture has already been squeezed out. So what this is saying is, as the atmosphere warms, you're going to be able to hold more water vapor. And that makes perfectly good sense. So, yeah, as the atmosphere would get warmer, you'd be able to hold more water vapor. And then if you can hold more water vapor, that would likely increase the amount of water vapor you could be holding in an atmospheric river event. And then you would get more rain, or it'd just be a more intense rain event once that atmospheric river comes in. Hadn't really thought about that, but that's pretty interesting. So we'll go on to read more, but that could be viewed as a good or a bad thing. Because, from a wildfire perspective, my main concern is always, I want California to get some more rain. So from that aspect, it'd be good. But then it's also bad when you think about things like flooding and catastrophic damage to life and property, which is what we were reading about earlier with atmospheric rivers. So let's keep reading here. This means that atmospheric rivers may become more frequent and more intense as a result of climate change. Studies have shown that atmospheric rivers are becoming more common in some regions, while in other regions they are becoming less common. In addition, the amount of moisture transported by atmospheric rivers has been found to increase in some cases. So that kind of ties into what we were saying. If the atmosphere warms up, it can hold more water vapor. So then the amount of moisture you're transporting with these atmospheric rivers would increase. Seems to check out. However, more research is needed to fully understand the extent to which climate change is affecting the frequency and intensity of atmospheric rivers and the potential impacts of these changes. It is important to note that the relationship between atmospheric rivers and climate change is complex, and other factors such as natural variability and changes in atmospheric and oceanic circulation patterns may also play a role in the frequency and intensity of atmospheric rivers. So I think that's a good thing to remember whenever you're talking about these things. It's always tempting to just have like an easy answer. But when it comes to the atmosphere, it's very nuanced. Like, this is something I've noticed with wildfire, where we have these very bad wildfires, and everybody kind of wants to just like pin it on one thing, where you'll see an article where it says, this is why wildfires are being bigger, or getting bigger. And another article will say, no, this is why there's more acres burned. But the fact of the matter is oftentimes all of those articles are right, because there's lots of different factors leading to wildfire, or the increase in wildfire. And that was actually the number one thing that my master's thesis studied, was I put it at lots of different variables in a machine learning model, and then I actually rank ordered what were the most important factors leading to the increase in wildfire danger. And fuel moisture, soil moisture, and max temperature were the top three. Fuel moisture being number one. And the scary thing was the trends in fuel moisture was actually the most alarming part. So there's at 10% fuel moisture, that's where we get those big extreme wildfire days. And below that, that's where the fuels are extremely dry. And on average, California is in that extreme threshold 55 more days per year than we were in 1980. So that's not exactly good news, but it was one of the most interesting things that I did figure out throughout my research. So yeah, I think that was pretty interesting information right there. I see there's a few people on the live chat. I see one of our other moderators, Frank, has shown up. If anybody has any questions you'd want me to look up, I think we've pretty much wrapped up the atmospheric river section. So that was the main thing that I wanted to look into today. So if anybody else has another weather topic, hopefully California related, then we can check it out. But in the meantime, I'm going to expand on this further. And let's see. I'm just going to say, what can you tell me about flooding in California? Because I think flooding is another aspect that I don't know very much about. It's kind of something that's true about academia, is as you go up in academia, you actually end up learning more about less. So I just got my master's in meteorology, but most of what I learned about was all wildfire. So I might know a whole bunch about wildfire, but when it comes to other stuff like, I don't know, atmospheric rivers or hurricanes or tornadoes, don't know as much as I should. All right, so we looked up, what can you tell me about flooding in California? So California is a state that is vulnerable to flooding due to its location and geography. State is situated along the Pacific coast and has many rivers and streams that can overflow their banks during heavy rainfall. So let's try to look up a California river map, because it actually is amazing to see just how many different rivers there are in California. I think that's a good one. Yeah, so I'll try to make this bigger. It almost looks like, it almost reminds me of like a body where you have all the veins and I think it's like called arteries. I didn't take, what is that, biology? I don't know. It almost kind of reminds me of that. It's just like these rivers are like the lifeblood of California and they just go through all the different parts of the state. So it makes sense that tying in what we were learning before, when you get one of those huge atmospheric river events that's transporting about as much water vapor as 7 to 15 Mississippi rivers, all of that water has got to go somewhere, and then a lot of these rivers are going to flood. So coming back here, flooding in California can be caused by a variety of factors, including intense rainfall, snowmelt, and dam or levee failures. In recent years, climate change has also been a contributing factor to flooding in California, as the state has experienced an increase in extreme weather events such as heavy rainfall and snowfall. So the first question you might be asking was, where was all this rain and snow in California recently? But I think the point that they're making here is that we might get less events overall, but the ones we do have are more intense, so then it leads to more flooding. So I'll try to phrase that another way. Overall, we get less rainfall, but the rainfall we do get comes in short, intense bursts, so that's where it can lead to flooding. That's maybe the next question that we have to ask this thing, because that's something that I've heard a lot of people say, but I've never actually looked up the science behind that. So Let's keep going here. Flooding in California can have severe impacts, including damage to property and infrastructure, loss of life, and disruption to transportation and other essential services. That makes sense. In addition, flooding can also lead to other natural disasters such as landslides and mudslides. So that's the one that ties into something that I do know about, which is wildfire. And that's where when you get a wildfire, think about what holds a hillside in place. It's all those root systems. In some cases, the roots from a plant can go down like 10 to 20 feet. And it's almost just like, I think scaffolding is the right word. It's almost just like holding that hillside in place. So when you get a big wildfire that comes through, kills the plants, then the next time you get a rain event, there's nothing holding that hillside in place, and you can get what's called, I think it's called liquefaction. Let's look that up. Liquefaction. Pretty sure that's the right word. Liquefaction takes place when loosely packed, waterlogged sediments at or near the ground surface lose their strength in response to strong ground shaking. Okay, that was wrong. That has to do with, I think, earthquakes. I'm thinking soil saturation. So the soil water content at which all pore space is filled with water corresponding to a water potential of 0 MPa. Yeah, that's a little wordy. Basically what I'm trying to say is you get a big rainfall event, your soils become saturated, which means they are holding as much water as they possibly can. If a wildfire burned out all the vegetation, there's no longer any roots holding that hillside in place, and it can basically just turn into a liquid, which turns into a big mudslide or landslide. Not sure what the difference is between a mudslide and a landslide. To reduce the risk of flooding, California has implemented a number of measures, including building dams and levees, implementing flood control projects, and enacting strict building codes and land use regulations. In addition, the state has a comprehensive emergency management plan in place to respond to and recover from floods. That's a little bit less on the science aspect of things, more on I think that's sociology. Despite these measures, flooding continues to be a significant threat in California. It is important for residents of the state to be prepared for the possibility of flooding and to take steps to protect themselves and their property during flood events. This can include an emergency plan in place, keeping an emergency kit on hand, and staying informed about flood risks and warnings. See, Lucy just said something in the chat. Just remember Sonoma County as a kid, 50 years plus, it rained for 2 weeks straight. No one freaked. Steady rain, occasional downpours, water up, water down. In the 80s, it became a river. And then Lucy said, I only saw beavers. We had river otters there. That's one of my favorite things about Santa Cruz. Every time I go out surfing, there's just otters popping up. They'll flip onto their backs, and they use, I don't know what they're eating. It's like clams or oysters or something. And then they hold a little rock, and they'll actually bang the rock against their chest or against the clam that's on their chest, and then they eat it. It's pretty cute. But that was kind of a tangent. But just getting back to here. So, okay. Yeah. Are there different types of flooding? All right. So this is, I think I had read somewhere else that there's 4 different types of flooding. So this says, yes, there are several different types of flooding that can occur. River flooding. This type of flooding occurs when a river or stream overflows its banks due to heavy rainfall or snowmelt. So first one, that's like that map we're looking at of California with all the rivers. Get a bunch of rain. Those rivers are going to overflow their banks. And then it can also happen when you get heavy rainfall or so snowmelt too. So then we also have flash flooding. This type of flooding occurs very quickly, often within a few hours of heavy rainfall. It can be caused by a variety of factors, including intense rainfall, dam or levee failures, and snowmelt. So I think flash flooding, that's the one you often see videos of in Arizona, where it's super dry ground. It's not able to absorb all that much water, and then they just get a ton of rainfall, and then it all just comes rushing down all at once. So often within a few hours of heavy rainfall. Yeah, that makes sense. Then you also have coastal flooding. This type of flooding occurs, I'd imagine, near the coast when seawater rises above the normal tide level and inundates low-lying coastal areas. So that would be, sometimes we get this in Santa Cruz. If you get a big king tide, that's probably the next thing I should look up. What are king tides? When you get a big king tide on the high tide, a lot of times the ocean will just be so high that you get, in this case, what we're calling coastal flooding. So coastal flooding can be caused by a variety of factors, including storms, high tides, and sea level rise. Okay. Urban flooding. This type of flooding occurs when heavy rainfall overwhelms the capacity of urban drainage systems, causing water to accumulate on streets, parking lots, and other paved areas. So that one's associated with heavy rainfall. And then slow onset flooding. I've never heard of this one. This type of flooding occurs over a longer period of time. Makes sense, it's called slow onset. And can be caused by a variety of factors, including prolonged periods of heavy rainfall, snowmelt, and rising sea levels. So then it says, it is important to note that flooding can be a complex and multifaceted problem. Different types of flooding can have different impacts and require different responses. To effectively manage the risks and impacts of flooding, it is important to understand the specific causes and characteristics of the different types of flooding that can occur. All right, so what are our 5 main types? We've got river flooding, flash flooding, coastal flooding, urban flooding, and slow onset flooding. Okay. I think those all kind of make sense right there. I'll just try to summarize that again. This is what I'm trying to do. I'm trying to kind of research this different stuff and then do like a quick summary, and then research something else, do a quick summary, and then just keep doing that over and over again. And I just figure if I do this every single day, I'm going to learn a fair bit about weather, and it's kind of more of a fun format to learn, because I try to just like sit down and read a weather textbook, but it gets boring fast and it's just hard to get myself to do it. Whereas this, it's kind of more interactive. I'm looking at the live chat. We're talking about river otters, all kinds of stuff. It's a bit more fun than just reading a textbook by myself. All right, so let's try to summarize what we just learned. There's actually 5 different types of flooding. You have river flooding, flash flooding, coastal flooding, urban flooding, and slow onset flooding. So river flooding, that's pretty understandable. You just get a large amount of rainfall or snowmelt, rivers overflow. With the flash flooding, that reminds me of Arizona, where they pick up a massive amount of rainfall in about 3 hours, and then you just see it rushing down. It often can lead to some very dangerous situations because it can happen very rapidly and people don't see it coming. And then coastal flooding, that can happen for a number of reasons, including storms, high tides, and sea level rise. Big one I always see is the high tides, where it just comes crashing in over the banks. Urban flooding, heavy rainfall overwhelms the drainage systems, and slow onset, where you've been picking up a large amount of rainfall for a long period of time. So I think those are all pretty interesting. I said I wanted to look up king tides next, because that's another one of those phrases I'll use, but I don't actually know what that means. What is a king tide? And we might need to look up a picture of this as well. Usually pictures are an easier way to understand something. While it's typing it out, let's look up a picture. King tide. So it's a popular non-scientific term people often use to describe exceptionally high tides. King tide is a non-scientific term people often use. Okay, tides are long period waves that roll around the planet as the ocean is pulled back and forth by the gravitational pull of the moon and the sun as these bodies interact with Earth in their monthly... So that didn't really provide that much information to us. Let's check out images. Ooh. So, what causes tides? This is what I was looking for. This kind of picture right here. All right, so tides are caused by the moon and the sun's gravitational pull. And it's literally pulling the water off of the earth. Or it's not off of the earth, but it's like, kind of. It's sort of, what causes tides? I think this will word it better than I will. In the meantime, let's look up what it's saying about king tides. So, a king tide is a natural phenomenon that occurs when the alignment of the earth, moon, and sun results in a particularly high tide. So that's kind of this picture right here. You're getting your gravity from the moon and your gravity from the sun. And an interesting fact I do remember about this is the gravity from the moon and the sun that Earth feels are actually pretty equal, because the moon is a lot smaller, but it's a lot closer. And then the sun is a lot bigger, but it's a lot farther away. So the overall pull of each of those is relatively similar. So, and these high tides are often referred to as king tides because they are the highest of the year. King tides occur when the gravitational pull of the moon and sun combine in a way that amplifies the normal tidal range. This can cause the tide to be much higher than usual, sometimes reaching levels that are several feet above the average high tide. King tides can cause low tides to be lower than normal. That's actually something I saw in Santa Cruz the other day. It was just about the lowest tide I'd ever seen. I was going for a paddle and I had to basically walk out to the spot that I usually surf. And that's just how low the sea level was. So king tides have a variety of impacts on the coastal environment and communities. They can cause flooding and erosion in low-lying areas and can also affect water quality by stirring up sediment and pollutants. That's kind of interesting. Didn't know about the pollutants aspect. But it does kind of make sense. Like I've surfed on some days with really big tidal swings, and the water first thing I notice is how much it's moving around. But then it also just seems a little bit like frothy. That might be a surf term, but yeah. I'm not a fan of surfing on big tidal swing days. Especially when I used to surf Ocean Beach in San Francisco, because you would just get all of this water rushing out of the bay. And if you started surfing at like North Ocean Beach, there'd be so much water rushing out of the bay that it would pull you like a mile or two down the beach. And then you'd have to walk all the way back up to your car after surfing. Very tiring. So in some cases, king tides can also cause damage to infrastructure such as roads and seawalls. King tides are a natural occurrence and are not caused by human activity. However, climate change is causing sea levels to rise, which can exacerbate the impacts of king tides and make them more frequent and severe. Makes sense. As a result, it is important for coastal communities to be aware of and prepared for the potential impacts of king tides. So just another little story about king tides is we had a big king tide in Santa Cruz the other day, and I wasn't surfing because I partially tore my Achilles, so I've actually been out of the water since Labor Day, at least surf-wise. I've still been going for paddles and stuff to stay in shape. But I was driving along the beach and I just saw like 200 people on the cliff, all looking down at the water, and I was like, man, like what's going on? So I parked my car and I go along the cliff, and there's just lifeguards hanging out at this one staircase, and there's just waves crashing into the stairs. It's pushing over like big rocks. It's just pure chaos. And all these surfers that are trying to come in are having a very difficult time. They don't want to get smashed into the cliff or any of the rocks. So the lifeguards, for every person that tried to come in, the lifeguards would have to go out there. They'd get their board. They'd help them in. And then there was just like 200 people on the cliff watching all this go down. It was quite a sight to behold. And this was at Pleasure Point in Santa Cruz. So this next one. So king tides, what did we just learn? It's basically when the sun and the moon both line up, and it causes the tides to be more extreme than usual, and that can lead to things like flooding. So let's look at this next one because this can answer our next question. Tides are caused by the gravitational forces of the moon and the sun acting on Earth's oceans. Gravitational pull of these celestial bodies causes the oceans to bulge, creating high and low tides. So the high tide would be when it's lined up with the moon. The low tide would be like over the middle of the Earth right here. The water's being pulled to the other places, so it must be lower in that area right there. So the moon has the greatest effect on tides because it is much closer to the Earth than the sun. Oh, that kind of went against what I said earlier. I thought they were relatively equal because the sun's so much bigger. Gravitational pull of the moon causes the oceans to bulge on the side of the Earth facing the moon and on the opposite side of the Earth. It's interesting it's on the opposite side of the Earth too. You'd think it would almost be pulling the water away from that side. Interesting. Wouldn't have guessed that. This creates 2 high tides and 2 low tides each day, also known as the tidal cycle. Oh, that makes sense. Because whenever you're looking at tides for surfing, they're 6 hours apart. And then, so that means you have 2 high tides, 2 low tides per day. And then the moon goes around the Earth once per day, right? That is definitely a question I should know. Does the moon go around the Earth once per day? Oh, it's maybe not the... So the moon takes about 1 month to orbit the Earth revolution, but 29.5 days to change from new moon to new moon. As the moon completes each orbit around the Earth, both Earth and the moon are moving around the sun. Okay, so it takes about a month for the moon to go around the Earth, but the Earth is also spinning, and we do 1 full spin per day. So if the moon barely moves and we do a spin, it does make sense that we'd have 2 high tides, 2 low tides per day. That's a little confusing, but it also makes sense if you think about it. All right. So the gravitational pull of the sun also contributes to the tides, but to a lesser extent. Sun's gravitational pull causes the oceans to bulge on the side of the Earth facing the sun and the opposite side. So when the sun and moon are aligned, their gravitational forces combine and can result in particularly high or low tides known as spring tides or neap tides, or as we looked up earlier, king tides. Tides are an important natural phenomenon that affect the movement of water in the oceans and can have a variety of impacts on the environment and human activities. Understanding the causes of tides can help us better predict and prepare for their effects. All right, so why does the ocean bulge on the opposite side of the moon? Interested to see what comes up with there, because that doesn't make sense to me. It seems like it would be pulling the water away from that side, and you wouldn't have a high tide there. But clearly that's not the case. All right, so I'm going to take a sip of water before reading this. So the ocean bulges on the opposite side of the moon because the gravitational pull of the moon acting on the Earth's oceans. Gravitational pull of the moon causes the oceans to bulge on the side of the Earth facing the moon and on the opposite side of the Earth. This creates 2 high tides and 2 low tides each day, known as the tidal cycle. So my gravitational force of the moon acts on all masses, including the oceans and the solid Earth. However, the Earth is much more massive than the oceans and is less affected by the gravitational force of the moon. That's a good thing. Could you imagine if the ground changed as much as the water with the tides? And I don't think we'd be able to build anything if that were the case. However, the Earth is much more massive than the oceans and is less affected by the gravitational force of the moon. As a result, the Earth's surface is not significantly distorted by the moon's gravitational pull. That's good. In contrast, the oceans are less massive and are more affected by the moon's gravitational pull. So this causes them to bulge. And the gravitational pull of the moon is stronger on the side of the Earth facing the moon, resulting in the higher tide on that side. The gravitational pull is weaker on the opposite side of the Earth, resulting in a lower tide on that side. Huh. So that kind of goes along with what I was thinking it would be. Gravitational force of the moon and sun combine to create the tides, with the moon having the greatest influence, understandably. Okay. So, don't know if that answered our questions. Let's see. Huh. Yeah, I don't know. That does make a whole lot of sense to me. I understand why that one would be a high tide. I understand why those would be low. I guess maybe it just forms an ellipse. Maybe it has to do with some kind of properties of water. Okay, I'll buy it. we'll take it. Could maybe do a quick little summary of what we've learned about tides. So, what did we learn about tides? So when it comes to tides, sorry, I'm going to clear my throat. When it comes to tides, you have 2 high tides and 2 low tides per day. And what causes the tides is primarily from the gravitational pull of the moon. So when you think about this, the moon is next to the Earth and it's actually pulling the water closer towards the moon, creating that high tide, and then low tides in the places that aren't being pulled by the moon. And then you also get some effect from the gravitational pull of the sun, but that's not as big of an effect as the moon. Then the biggest tides that you can have, the biggest tidal swings, is when the sun and the moon are aligned and they're both using their gravity to pull the Earth's water. And that's where you can get what you call king tides, which is something that I saw the other day at the beach where lifeguards were having to rescue surfers because the waves and the ocean were just crashing against the cliff, and it was a pretty dangerous situation. All right, so I think that is about how much we're going to learn today. I'm probably going to do this again tomorrow. I thought this was kind of interesting and fun, and it's a more fun way for me to learn than just reading a textbook by myself. I also like seeing the live chat, so thank you to the moderators for keeping our live chat nice and good. And if you're new to the live chat, some of the things we looked up, if you want to go back and watch it, atmospheric rivers, we looked into flooding, and then finally we looked into tides. We also talked wildfire a little bit, but that's because I can just always talk about wildfire. So probably see you all again tomorrow, and thanks for watching.